So we begin the workshop with a talk by Professor Martin Berzins, Martin of the Uintah framework. That's what many of us know him for now. But to go back, he just like Ed said, he was a postdoc here. Well, probably began as Martin probably began as a grad student at Leeds and rose up to the Dean of Engineering at Leeds in UK, and then in 2003 he came to Utah and then has been involved with the Uintah framework and various things. And we pride ourselves. What do we do in our group? We think of it as, well, it's hard to describe, maybe software engineering, maybe abstractions in parallel computing. We're not, and when we say we are computer scientists work in parallel computing, people think we are numerical methods. People say, no, we don't understand them. We understand parallel programming abstractions and performance issues and so on. And so then we collaborate with people who do numerical methods. We collaborate with people who do applications. And Martin is all those things rolled into one. He's an applications person, he's a numerical methods person, and he's a parallel programming abstractions person. So there's a lot more to say about him. I'm only going to say that his recent focus has been on combustion-related problems and multi-scale material modeling, I believe, and problems associated with that, and a diverse collection of other problems which are extremely broad in nature. Maybe he will tell you a little bit more about that. Well, I should set your...
Okay, great. Well, thank you for the introduction. It's great to be here. This is very loud. This isn't going to work. To be here. Thank you for inviting me to give this talk. I've been a great admirer of the work that's done here for a long time. This is an amazing place, fantastic building. There's so much going on. It's a great center for computer science and for multidisciplinary work involving computer science. Okay, I'm going to talk about sort of task-based frameworks. This is bad. Okay, all right, okay, so that sounds good to me too. Okay, so I'm going to talk about, so we're starting a little bit late, so I'm going to talk about really, there's a lot of interest right now in these task-based systems, as Sanjay said, and a lot of hype, actually. And so what I want to do is to take a sort of critical look at what we're doing and try and understand what's good about it, where the strengths are, where the weaknesses are, and so on, and to discuss some of the work that we've been doing in Utah with these approaches, work that's kind of complementary and similar in some ways to the work that's done here, but has a different slant and very many different details as regards implementation and algorithms and so on. So I'm going to talk about the sort of some background, talk about the history of these methods, talk about the Uintah code, kind of talk about one of the problems that we're tackling at the moment and where we are in dealing with some of the challenges that the new architectures have sort of brought us to think about. Lots of people deserve acknowledgements for funding, DOE, especially Army Research Lab, NSF, Insight, Exceed, and so on. And we're very grateful to both the funding and the compute resources. So the key thing is that peak computer power grows by a factor of 1,000 every decade, and this really has a very deep and lasting impact on our ability to do science. At the same time, our codes change. We've had code extinctions, in fact, if you look back. You're moving from vector machines to the sort of, the killer micros, if you like, and then we stuck with a kind of MPI model for quite a long time, and it looks like there's a fairly significant change coming as we go forward in the future to GPUs and things like the Xeon Phi and so on. And the question is, will our code survive? What will survive? And really what I want to try and look at is whether or not task-based approaches are a key technology for this. I also want to talk about things like the hype that's attached to ideas to a certain extent as well. So the vision for software perhaps comes from, well, from many different people, but a good example is Bill Harrod's comment at SC12. The traditional model we have of communications compute is broken. We can't do anything more with it. And then the idea that people have engaged with and the sort of the romance is, in some sense, the idea that at Exascale, we're going to have these task-based approaches, and the Exascale report in 2008, 2009 describes this very well. We're going to have prioritization of critical path and non-critical path tasks, adaptive DAG scheduling of tasks, and so on. So this graph-based idea. But on the other hand, there are other people, and this is from a parallel processing award winner who I'm going to keep anonymous, said that this has always been a bad idea. It was a bad idea when it was introduced. It's a bad idea now. So there's a mixture of views about how useful this is, and it's important to understand how strong these ideas are and what their strengths and weaknesses are. If we look at the history, the ideas behind task-based approaches go back to the 1960s. And it's quite interesting to read Vivek Sarkar's thesis, which came out in about 1989, where he talks about many of the things that we are now using. And I guess this work was done in parallel with the work that Sanjay started around the same time. I don't know who influenced whom or whether these were separate streams of development. Maybe Sanjay can tell us that. And anyway, so data flow execution, compile time, cost assignment and scheduling, graph-based representations. Here's one that I sort of lifted from his thesis, one of the examples he was looking at. And then you go to Charm++, and of course this has had a deep and profound influence in terms of how we think about these approaches and how useful they are. And I came to Utah in 2003, and at that time the effort there was very strong, funded by the C-Safe Center was funded by DOE in the ASCII program. And the Uintah code was developed, and Steve Parker developed this code. And I asked Steve recently, I said, well, did you guys know about this? And he said, no, we were coming from the sort of ski run idea of graph-based tasks linking them together, and we sort of developed this independently to a certain extent. It wasn't until they got reviewed that they found out about Charm++. So it's interesting how these ideas have developed in parallel. At the same time, Vivek Sarkar has also been pushing work that goes back, I guess the origins are back here. And there are many recent developments as well. There's a CNC language, there's some Thomas Sterling's Parallel X, and so on. So there's many things going on right now, so lots of activity. At the same time, this activity has to be focused on future machines, and as Ed pointed out, the next generation of machines, the Coral machines, have been announced, and they range from the Summit machine that's coming in at Oak Ridge to the Aurora machine that's coming in at Argonne. Two very different architectural styles. Aurora is going to have something like 50,000 nodes, and Summit will only have 3,500. Summit will have GPUs, and Aurora will be based on the Knights Hill Intel processor, and those are coming in 2018. There's a clear plan for DOE to go out to 2018. The Exascale initiative goes out to 2024 if funded. It's not at all clear what NSF or Department of Defense are going to do in that time frame. There are no real plans with the same sort of scale or the depth that the DOE has at the moment. The key thing really is that energy is perhaps the defining issue, and that means that we're moving to different modes of computation, and that means that we seem to be going towards accelerated GPU-type architectures because of this energy requirement. 2024 is still a long way off, and things may change. It's not clear what companies like ARM are going to do, so we'll see. But anyway, as we go to over the next 5 years, systems like the Coral systems, Summit and Aurora, are based on the Xeon Phi and on GPUs, and so we'll have to adapt our programming models, and we have been doing so already, to work with these architectures. For those of you who haven't seen these architectures, and I guess many of you have, I mean, the Intel Knights Landing that's coming out towards the end of next year, really, or I would think. It's not clear entirely. 72 cores, large vector units, 4 threads per core, grid-type structure now, as opposed to the present Knights Corner system, and arguably this is going to be a very powerful engine. We'll see. It's a basis for the next 2 big machines for sure, but not a lot's known about how useful it's actually going to be for real computation. At the same time, if we go to GPUs, you look at NVIDIA's Pascal architecture, going down to 40 nanometers. maybe using things like 3D memory, unified memory between CPUs and GPUs, NVLink, fat pipe between CPU and GPU. One of the challenges with the GPUs, as those of you know who've worked with them, is that you really are feeding the GPU through this very thin straw, the PCIe bus, and the difficulty really is in making use of the GPU to its full extent, given the fact that communication is slow and you have to essentially preload tasks and do things like that. The NVLink will help a lot when it comes to speeding up communications, but the GPUs themselves are getting faster, so it's not clear that the communications are getting faster or accelerating in some sense compared to the actual speed of the GPU. And at the same time, you're going to get this if you link to ARM or IBM, not if you link to Intel, as far as I know. So there are some challenges in using these architectures still. Okay, so we've talked about the background, the ideas. We've talked about the machine challenges that we have to face. And there's a lot of excitement about the approaches that we use. I try not to oversell things when we think about how we, when we write code and when we say what we can do. And we have to look at this challenge of making sure our code persists throughout the next decade. And an example of the sort of comments that you get is that in our review for our Utah Center just recently, one of the DOE reviewers said, well, isn't it enough just to have an asynchronous approach that's going to solve all our problems? And the answer is not on its own, probably. There has to be a lot more underneath it to make these approaches work. And the nice thing here is if you look out in the history of ideas, you'll see that there's a hype curve. And here's the hype curve. Here's the technology trigger. Here we get really excited about what's going on. We get to the peak of inflated expectations. And then everybody realizes that this stuff doesn't deliver what it's supposed to deliver. So we go down into the trough of disillusionment. And then finally, we understand what can be done, and we get to some level of productivity. So the question is, where are we now with task-based methods? Have we been through this? Are we still on the way up with exascale and so on? It's interesting to speculate. So I think it's important to understand what these methods do and to understand how strong they are, but not to say that they're going to solve everybody's problems overnight, because there's more to it than that, as I hope to show you in this talk. If you want to interrupt with comments and questions, please do, actually. Okay. So in order to show how these ideas work and what the challenges are and what the strengths are, I want to talk about the open source software, the Uintah software that we have in Utah. This software was developed starting in 1998, as I said earlier, went through the sort of 2 rounds of DOE funding, and was largely sort of an internal activity. It wasn't really released very much and so on for a number of different reasons, some going down to the application space that it tackled. And since about 2005, we've pushed the software out and used it, really broaden the application base and use it for many different problems. So it's important to think about the people involved who are doing this, because we're talking about sustainability and so on. What we've done is, in the same way as here, put together a number of different sources of funding from NSF, from DOE, and a number of graduate students have made key contributions. Of the work, the scalability work I'm going to talk about, Qingyu Meng, who's now at Google, and Justin Luchens at NVIDIA, have been absolutely key. They're the graduate students. Jacqueline Beckvermit is running the explosion problems I'm going to talk about. There are developers, Alan Humphrey, John Schmidt, Todd Harmon, who are sort of hold things together. Alan has been doing the radiation work I'm going to talk about. John Holman has been working on the Xeon Phi. Dan Sunderland has joined us from Sandia. And we have a bunch of people working on another NSF project. So this is a sort of some of the group who are working on the Uintah software and who've contributed to the things I'm going to talk about. The model that we use is that the developers kind of provide a base, and the graduate students do many of the really innovative things that turn out to change how we can scale and so on. And so Qingyu and Justin And Alan, when he was a graduate student and so on, have been key in this, and then John will be in the future, I'm sure. So what are the main strengths of the task-based approaches? Well, one of the main strengths is actually the sort of separation of concerns, in the sense that we can separate out specification and implementation in many ways, and execution. So if you look at the Uintah software, what we've done is we have a bunch of applications codes. These applications codes range from the ice fluids code, the material point methods code, applying particle methods to solids, the Arches combustion code that's used as part of our PSAP project. We have a domain-specific language, and so on. And these generate a task-based description of what we want to solve. And this task-based description is then kind of compiled into, whether it's into C++ or CUDA, and then it's executed in an adaptive fashion using the same ideas that Sanjay talked about, over decomposition, for example, work stealing, overlapping communication and computation. All these ideas are central to the execution of these task-based models. And then what we do is we also have an intermediate layer now, which we're working on, which is built on the COCOS software that comes from Sandia, that Dan Sunderland is involved in, and then execute on GPUs, CPUs, Xeon Phis, or whatever. This sort of layered abstraction is very, very important, because it means that the applications themselves, the applications codes, don't change. It's the runtime system that changes as we move to different architectures. And so the comment I have here is that some components have not changed as we've gone from 600 to 600,000 cores. Same code at applications level. Not entirely true, because we've taken a few bugs out of this, but essentially true. And that's one of the key things about this approach, is that you can write applications code that doesn't have to change when you change architectures. Okay, so what do our codes do? Well, originally, this code tackled a sort of relatively narrow class of problems in some sense, in terms of the kind of numerical methods that are used, but a broad class in terms of applications. And so the basic abstraction is just a patch with cells and with particles. And the question is, you'd ask yourself and say, well, how broad can this be in terms of what we can solve? Well, because the particles used to represent solids and fluids, if necessary, we can solve all kinds of crazy problems with crazy geometries and so on. And the ice code is the fluids code that I mentioned earlier. The particles are the material point method code, and the Arches is the combustion code that I talked about, with radiation models and linear solvers and so on. There's essentially a structured grid approach with unstructured points on top of it to patch-based decomposition, and we use mesh refinement. The mesh refinement that we use is a sort of regular tiling approach, whereby any cell that's marked for refinement is just immediately refined. We don't use it. We've moved away from trying to use algorithms like the well-known Berger-Rigutzos algorithm, for example, because it doesn't scale. And we've been able to get this to scale out to many hundreds of thousands of cores, even with combinations of fluids and solids and mesh refinement using the approaches I'm going to talk about. We have dynamic load balancing to tasks migrate. We profile the performance of each particular node and core. And we forecast its future performance, and we use a sort of time series approach to predict what's going to happen. We use a space filling curve to do the original decomposition. And we have this combination of MPI and threads, essentially. We also have an MD component. We're trying to do work with the Army on multi-scale modeling, where we couple continuum approaches with molecular dynamics approaches. So the task-based approach that we use is that each task defines its sort of computation with the inputs and outputs it's going to use. There's an example of a task graph here coming from the ICE code. This information is used to create a graph where the work is at the nodes and communication is along the edges. The tasks themselves, as you'll see in the next slide, which defines a programming model a bit more precisely, really don't explicitly define communications. They only define the information that they need and the information that they supply back to a data warehouse. Obviously, we overlap communication and computation, and we execute this task graph adaptively and sometimes out of order by saving inputs to tasks. So in summary, tasks get data from an old data warehouse and put results into a new data warehouse. The data warehouse exists on a node and is used as a sort of central storage mechanism. The programming model that we use looks something like this then. Imagine a stencil computation where we have our patch and we have halo information or ghost cells, if you prefer to use that term, in green, the central patch in blue. A task essentially gets the core information that's attached to the patch. We call this UOLD in blue. The halo information which comes in across the network, which is set up by the sort of system of computes and requires, which is translated into MPI commands. So we bring in halo information, we send out halo information. That's done at the data warehouse level. The user code doesn't see any MPI, so we could take out MPI completely and replace it with something else if we chose to. And what happens is that the solution information plus the halos is passed into the task. The task does its computation, so U in this case is defined as some time stepping of some broad function, stencil function of UOLD and UHalo, and then we put UNew back into the new data warehouse, which then becomes the old data warehouse for the next step. So the abstraction that the task sees is very simple. It just specifies what it wants. That comes in from the data warehouse. It does what it needs to do. That's put into the new data warehouse. But of course, you can then also take things from the new data warehouse, and I've simplified matters greatly. But that gives you some idea of what the central abstraction is that's employed. If we go back to the tasks, if you look at these tasks, for instance, this structure is really pretty simple. And so when I was giving a talk once, somebody said, well, I don't really understand how this stuff works because your tasks are pretty, your task graphs are pretty simple. It's not clear that you have the parallelism in those. Well, the reason that we can get the performance that we get in terms of being able to scale and so on and run very large, complicated problems in a good fashion is that on each node we have multiple task graphs. So we have multiple patches, and this to some extent is the over-decomposition that Sanjay talked about. And the halos connect these patches, but each node has its own task, each patch has its own task graph, so there are multiple task graphs on each node. And this, in some sense, might be, you almost think of this as, I call it the task graph soup. This soup exists on a node, and the individual cores can then pick from the individual tasks in a way that makes it possible for tasks from one patch to execute on different cores, for example. And the nice thing about this is as the task graphs get more complicated, the richness that you have from that means that it becomes easier, not harder, to schedule things. So in the very complexity of the graphs, the thing that might be a problem actually makes life easier in terms of overall scheduling in some ways, providing you don't just have one single very complicated graph. So this is important in terms of getting performance. At the same time, I'm very careful to say that this approach is not the DAG approach is not a silver bullet. If I look back at how our code has developed, there have been several distinct stages. So until about 2005, there were static task graphs, standard data structures, one MPI process per core. AMR didn't scale very well. The second, well, here are the old results from 2005. You see scaling out to about 1,000 cores, or same thing for an AMR calculation up to a couple of thousand and so on. You look at the next phase and you say, well, we improved our data structures. We've got AMR to scale to about 12,000 cores and 100,000 cores using this much simpler approach for adaptive mesh refinement. And then the data structures caused problems. We had to go to out of order and dynamic task execution to get the performance beyond that for the sorts of applications that we were dealing with. And then in the third phase, we've gone to a hybrid model. We have a threaded runtime system on a node, one MPI process per node, one data warehouse per node, multiple cores and/or GPUs grab tasks. When we have it's got linear, we use a hyperlinear solver for the applications that need that. So there's a lot of work in here, and just going to a task graph approach, which is kind of where we got to in 2005, isn't enough on its own. You have to have all these other things, and I'm sure that you have learned similar lessons in the work that you've done with your codes. So one has to be careful about the work that's needed to make sure that the runtime system delivers what it needs to do. But on the other hand, the applications codes haven't changed. So what does our runtime system actually look like? Essentially, the runtime system looks something like this. For a modern architecture, say with GPUs, or you can replace these with Xeon Phis, what we have on each node, each multi-core node with GPUs, is the following. We have a data warehouse for the CPU cores. We have a GPU data warehouse with communication between them. The CPU cores themselves basically run tasks, access information from the data warehouse, but they only run tasks when the tasks are ready. So we have a task graph stored on each node. We have a GPU task queue. We have a CPU task queue. And when tasks are ready, the CPU cores and the GPUs go and grab tasks, execute tasks, and deliver the results. So these essentially are data structures. The work is done by the individual cores and the GPUs with these task queues, and the data itself is stored in the data warehouses. Communication to the external network and MPI is done at the level of the data warehouse. So that's the model that we use for executing. And the trick really, the intelligence is in how you schedule the tasks and how you the algorithms that sit inside here for prioritizing tasks and so on to make sure that tasks run as efficiently as possible until the cores are not kept waiting. Okay, so I talked about the fact that we only have one MPI process per node. And for those who haven't looked into this, part of the reason for that is just storage. We were running out of storage with one MPI process per core. And there's an example here, an old example now, which shows what the problem is. If you think about all the buffering that's needed and the storage that's needed for the ghost cells, essentially by moving from a model in which you have individual patches with all their halos and what's needed to store that to a single model in which you just have everything together on one multi-core node with large halos, you essentially cut the amount of memory, in this particular case, almost by a factor of 2. If you go to Kraken, which is a machine that we did this on a long time ago, 98,000 cores, we only needed 10% of the memory in this model that we needed on this one. So huge saving in memory in going to this threaded approach. Challenge is making sure that all our codes are thread safe. Another challenge is in linking combinations of threads and OpenMP, for example, if some of the applications packages that we use that we work with use OpenMP. For instance, the linear solver that we use does. So that's a bit of a nightmare at the moment. So that's a great saving in terms of memory. In terms of getting execution, I mentioned out-of-order execution. With the task model that we have, we can execute tasks as soon as the information is there. And we don't have to necessarily execute tasks in order as long as we are careful about saving the outputs and are careful about how we structure the computation. So here's an example for one of the challenging fluid structure interaction problems I'm going to mention later, but I'll show you kind of what happens on 3 different machines. The machines are Titan, Stampede, and Mira. So Titan is a sort of Cray AMD machine. This is just using the CPU cores. Stampede is the sort of Intel machine at TAC, and Mira is the IBM Blue Gene at Argonne. So let me explain what you're looking at here. The blue line here would be the tasks executed in order as they're set up. Okay? The green crosses show you where the tasks were actually executed. So, for example, this cross here is a task that's numbered about 400 and something, executed at stage 1100. So the tasks below the line are all executed early, essentially. So we have out-of-order execution for those tasks. Because those tasks are executed early, the other tasks are executed late. So there's an example down here. If you have tasks 1, 2, 3, 4, and 5, if you execute task 4 early, it then looks like 2 and 3 are executed late. So that's why there are more crosses above the line than below the line. So this shows you the out-of-order execution on 3 different machines. It also shows you that the execution is different, because if you look carefully, you'll see while there is a lot of similarity between these execution patterns, the patterns are not identical. So the code executes differently on different architectures with different communications networks.
What's the given order?
Well, the given order is just as it comes from each of the individual graphs that the user specifies.
In some sense, that's arbitrary.
It's chosen by the user, yes. And there is a degree of arbitrariness about that, and that's what we're exploiting, in fact. And that's how we're able to do that, because it's not clear that the user will necessarily specify the tasks in the best possible order. But this is important for getting performance. And so I'm not going to dwell on all of the work that we did, but we talked about one MPI process, reduces memory. We keep rewriting the runtime system, as you guys do as well, I'm sure. We have to use optimal size patches to balance overhead and granularity. So here's an example. You see patch sizes, so this is like 8 cubed, 12 cubed, up to 24 cubed. And what you see here for the total execution time is that it's minimized around about 12 to 16 cubed for the architectures we were looking at. So patch size is important because it balances overhead. And you're seeing overhead here. Well, the task weighting increases with patch size because everything is more coarse-grained. Regridding and copying kind of drops as we increase size, and scheduling also drops as we increase size because there's less overhead. So these two are overhead. This one is a penalty that you pay for coarser granularity, and you see the sweet spot is round about here. The same thing with algorithms to prioritize execution. If you look here, we've got sort of random priority, first come, first served, patch ordering, and the last one is the most number of external messages. So we prioritize tasks that have to do external communication, and you see that the time drops from something like 300 with random execution to about 140 with most messages. So you have to prioritize tasks that have external communications, and that's an obvious lesson, and I think it's similar to something that you guys do too, but I'm not sure. Scalability, well, these are some of the results that we get. So we're looking at an example here of a blob of material moving through a liquid, and we're looking at different resolutions. So 2 resolutions, resolution B, which is at the top end, 29 billion particles, 4 billion mesh cells, 1.2 million mesh patches. We've got scalability on the strong scalability on Mira and on Blue Waters, out to about 768,000 cores on Mira, and a little bit less on Blue Waters. But you see good, strong scaling. This problem involves mesh refinement, fluid structure interaction, and so on, and we can get it to scale at these very large architectures with very large problems. Why are we interested in this? Well, if you look at the picture in the top corner, I don't know how clearly you can see that. It's quite a lot of background light here, but what we're looking at is a crater that's about 60 feet across and 20 or 30 feet deep. And the comment that I make is that driving around the roads of Utah is a somewhat scary business. And what somebody did was they decided to put an explosives factory at the bottom of the most dangerous road in Utah. Not a particularly smart move, perhaps. And what happened was the guy who was driving a truck. Now, these explosives are boosters that are used in seismic testing, so they're used in sort of oil and gas exploration, for example. And these boosters, the guy had a truck with 8,000 boosters, 2.5 to 5.5 pounds of explosive in each one. The truck turned over, caught fire on Highway 6, which is the most dangerous road in Utah statistically. Fortunately, there was another guy in the truck. He pulled the driver clear. An off-duty policeman stopped. The truck was burning. They ascertained what was in the truck. They cleared the area. And about 20 minutes later, this is what happened. Amazingly, there was no loss of life. The worst injury was just a few ruptured eardrums. But unfortunately, the road and the railway line were taken out. And we don't know why this really took place. This is our evidence from a transition from a deflagration to a detonation. A deflagration is where the explosive essentially burns. A detonation is where it all immediately goes off at once. The very great difference in wave speeds. So what we're looking at here is an example of, here are the containers, a side view of the explosive containers or part of them. And what we're looking at is the increase in pressure as burning starts from this corner. And we get to the situation here in red where the pressure rises to about 5 gigapascals, and then we get detonation. And what we're looking at here is a 3D calculation in red of the pressure rising in this sort of simulation to the point where detonation takes place at about 5 gigapascals. A couple of smaller calculations, axiometric 3D and 2D here. So we're able to model this problem with about 250 million hours of insight time on the mirror machine. And we're almost finished with this now. So we've been able to show that as to why this explosive should detonate in this case. And here's our, as I said before, here's our evidence for the detonation. Almost all the explosive was consumed. Very little was left of the truck. And we were able to do this by changes in the runtime system and the algorithms. So here's scaling results. We've got weak scaling horizontally on a log-log scale. So these lines, weak scaling breaks down a little bit as we go to 512,000 cores. Strong scaling, the time per time step drops as we increase the number of cores. Strong scaling lines here. Good strong scaling line out to about 512,000 cores. But this is only done by, for instance, improving the performance of the regrider and remeshing, improving the performance of some of the algorithms that we use to copy data, improving how we compile the task graph that's used to, as a basis for the calculation, and improving the performance of the total AMR time in order to get this scalability and to be able to run the problem. The final piece of this is that we've been able to show that had these boxes of explosives been stacked in a sort of checkerboard fashion, so one full box, one empty box, one full box, one empty box, this detonation would not have occurred. So, you know, this is a real problem, and we've been able, we think, to suggest an alternative method for avoiding this particular challenge. Or disaster, I guess is a better word. Okay, so let's talk about the work that we're doing now. This work is, that work is just about finished. We're doing the last runs right now on Stampede. What we're looking at now is a problem that comes from clean coal. Coal is unavoidably a source of energy that we will have to keep using. You know, as a species, we don't seem to have a way around it right now. But using coal in a clean and economical fashion is one of the things that is a central concern for many people, not just here, but worldwide. So what we're doing is working with a company called Alstom, who've just been big French company, just been taken over by GE, to look at a clean coal boiler. And when people talk about clean coal boilers, they say, oh, well, you might think about this and say, well, this is something you might put in your basement. This thing, well, you can see somebody at the bottom of this here. So this thing is about 60 meters tall, about 10 meters across the bottom or so. So to resolve this turbulent combustion problem on physical grounds, we need to get the grid down to about 1 millimeter. Okay? So we're talking about 9 times 10 to the 12 cells. It's about 1,000 times larger than anything that we can do right now to do a proper design calculation for this. So that's the focus of our center. And the work's been led by Phil Smith in the Institute of Clean and Secure Energy, and I'm the computer science lead. Here are the people who are involved. Even the president of the university has a piece of this. He's a coal guy, David Pershing. So these are the people involved. 3 different teams: computer science, predictive modeling, uncertainty quantification. Uncertainty quantification involving people at Berkeley as well as in Utah. I won't dwell on that. The algorithms that we use, are based on large eddy simulation. It's like almost like direct simulation for coal. So the idea is that we resolve down to a certain level and then use a model at that level. We have a finite volume code, basic equations of conservation of mass, momentum, and energy. There are all kinds of things in here. There's sort of tabulated chemistry. There are methods for dealing with particles. Particles are very important. There's a low Mach number approximation, so that means that we have a pressure Poisson solve, or something that's like a pressure Poisson solve, up to 10 to 12 variables in the full problem when we get there. Radiation is very important, so either we use a discrete ordinates approach to radiation, which involves large linear solves, or ray tracing, which is what I'm going to talk about here. Uncertainty quantification is key. So here's the kind of thing that they're doing. We have experimental results in red. We have simulation results in blue. And what we're doing is looking for the consistent results in green in the work that we do. So that's the approach to quantifying the uncertainty that they're adopting in this problem. Radiation is kind of where I want to finish off, because radiation is the key problem in the sense that radiation, as those of you from a physics background will know, is ubiquitous. It goes everywhere. That means that in a communication sense, everything is connected to everything else. We have global connectivity. How do we deal with that? Well, if we try and deal with it directly, things are not going to scale. So here's what we do. It has the coupling to CFD is relatively loose in some sense. Also, our colleagues in chemical engineering tell us. And the required resolution decreases with distance, so the possibility arises of using AMR. If we use the discrete ordinates method, well, that means large linear solves, but we can use ray tracing. So what we do is we essentially say, well, okay, if this is our CFD mesh, the fine scale down here, what we're going to do is use a radiation mesh that's fine around the region of interest here and coarser further away. So we use an AMR approach to define the radiation mesh. And what we do is we replicate the overall mesh on all the nodes that we have, and we can do that because we're just using coarse representations of it in certain places. And that means that the ray tracing itself is a local calculation, but we still have to connect things back together. So CFD level mesh is fine. Radiation mesh is coarse with mesh refinement. And what we do is then calculate the source term for the energy equation, which comes from radiation, using ray tracing. So this is the sort of usual finite volume stuff, and we have this extra term. And this term essentially involves the integration of the incoming radiation intensity around a sphere. So we have an integral to evaluate, which we can evaluate using, say, Monte Carlo methods or whatever quadrature rule you want to use, based on the rays that are coming into a particular cell. As I said before, global replication of the coarsened form of the radiation mesh on each node. So the ray tracing itself is a local calculation. So what does that look like? Oh, actually, something else as well. If we were to do this using the standard ray tracing approach, we'd have to take into account what comes into a particular place. What we do instead is we do reverse Monte Carlo ray tracing. So we trace back outwards from the region of interest to where the rays actually came from. So we incorporate all the sort of dominant physics for ray scattering and different kinds of media. We vary the number of rays per cell that are used. We replicate the geometry, as I said. We calculate the heat fluxes on the geometry. But then what we have to do is to transfer the information to do with absorption and scattering that's calculated locally now globally. So we still have a global aspect to the calculation. And I'm running out of time a little bit, so I'll just say that what we do is essentially we coarsen the mesh in the way that's sort of done here, as I showed earlier. So we have to send out this radiation information on the coarsened mesh. So we do a global all-to-all on the coarsened mesh and kind of local halo updates with the fine mesh radiation information. So what happens if we do that is we get some very nice scaling results out to, in this case, all the CPU cores on Titan. We're working on the GPUs right now. And what you're looking at here is the strong scalability of the radiation calculation out to about 260,000 cores. This line here is the MPI communication, and you can see it's starting to intrude at the end here. So we might have to use coarser meshes at some point in the future to keep the communication costs down. But anyway, we have radiation scaling out to all of Titan right now, and hopefully all of its GPUs. I'll skip the next slide, which just shows the communications volume, and show you the GPU results. Right now, they're a little bit primitive. We only go out to about 1,000 cores, 1,000 GPUs on Titan, but we've changed the algorithm since then, and we think that we'll be able to get out to all of Titan's 18,000 plus GPUs. If we try and do the same thing on the Xeon Phi, not going to skip a slide. On the Xeon Phi, the results are disappointing. The key takeaway is that the ordinary Xeon E5 outperforms a Phi by about 40%. Here are the CPU results. We're looking at the elapsed time. Here are the Xeon Phi results. The Xeon Phi results are pretty poor. We're going to have to go in and rewrite this code at a very basic level to work on the present generations of Xeon Phi processors. The results, I mean, and these are results that are not uncommon for other applications as well. Okay, so portability and node performance, just to finish off. I don't have a lot of time, except to say that what we're doing is looking at two different approaches. One is a domain-specific language, and the other is using an abstraction layer that maps loops onto a machine efficiently, and the one we're using is COCOS. Raja is an alternative. And the domain-specific language that we use essentially also uses a DAG to represent the physics. This is work from James Sutherland and Matt Might. James is a chemical engineer who's worked at Sandia on code. Matt's a computer scientist. So there's a whole bunch of information here, but essentially the bottom line is that we get good speedups. We can generate code for GPUs and Phis. The GPU code is not quite as fast as I would like just yet, but it's improving, and that's the approach that we're going to use to map the physics components written at a MATLAB level onto the GPUs. So I have a lot more material. I'll just say something about COCOS. COCOS is an approach that's come out of Sandia. Essentially, it's using template metaprogramming to essentially change the data structures that we use. So you can map onto different machines with different data access patterns. It's a sort of using standard C++, and it's in the spirit of all these other approaches here, and it's not a language extension, and it makes layout changes that are invisible to the user code, essentially, to get performance. So if you look at the work that Dan Sunderland has done with Carter Edwards, you'll see that they get quite good performance on the GPUs for this simple piece of molecular dynamics code. The Xeon Phi and the Xeon are pretty similar in some ways. This is using the correct layout with texture mapping for the GPU. So that's encouraging. So that's what we're going to do. And just to lead into one of the other talks here, we've also taken the Uintah approach and worked with Janine Bennett's group at Sandia. There was a 2-day porting effort. The Mini Aero app was rewritten using Uintah. In about 7 days, 90% of the core features were working. Out of the box, it scales to about 130,000 cores on Titan, and further work is ongoing by Janine's group to improve the performance of this. Okay, so I've run over a little bit, but summary, the abstractions are important for portability, scaling, if we're not needing to change the applications code. Scalability still requires a lot of tuning of the runtime system, and you can't develop nodal code in isolation because you have to take into account the local effects and what works globally. Future portability for running on these new machines. Approaches like COCOS and the domain-specific languages are very promising to get us to those new machines within that same task-based approach. A challenge for us still is things like the linear solvers and how we get those to work on these new machines because they're conspicuously lacking right now. And then I should stop. Thank you.
Hundreds of questions in my mind, but then I want to ask you
describing whatever they're available. So one aspect is stating that you limit our performance. So if you have a very over-decomposed task graph and every core is describing whatever is available,
Uh-huh.
at the end of the day, your data dependent, what happens to your data dependent?
Well, the cores only grab tasks that are on that node. They don't. Yeah, well, I mean, I think there are some issues there because you have to generate the code for the GPUs. And right now, for our applications, we have fairly specific things that we will run on the GPUs. And I mean, you know, if you look at a machine like Summit, for instance, 5% of the performance is going to come from CPUs. 95% is going to, you know, to all intents and purposes, the CPU is not very interesting anymore on those machines. Well, there are, and we'll have to schedule between those, you know, but I don't anticipate that being so much of a problem. But you're right. I mean, there are some challenges in dealing with these heterogeneous architectures, and I'm not going to pretend that we have all the answers right now because we're only starting to address that issue. What I can say is that I think that the approaches that we have are sufficiently general and flexible that we can change the runtime system, we can generate different versions of the code to run these tasks either on CPUs or GPUs. And, you know, I don't see that conceptually there are any huge difficulties in doing that, in dealing with that scheduling problem. But I'm not going to also tell you that I have the answer right now and that I know that, you know, it's going to work in exactly this way. But I don't see it as being conceptually a massive challenge.
In fact, runtime system, I believe, will be the only thing that has a chance of making the correct
Absolutely.
optimizing what's happening at runtime to minimize even the delay. As long as it takes into consideration that as a cost. But any other short question? Yes.
Well, what we do at the moment is both these methods I've talked about. The matrix language can generate the computer code for the task. We can also generate the CPU code for the task to generate the Xeon Phi code for the task. All those are different. The task itself. Well, it does look different because the task, the GPU task, typically has to take into our patches, for example. You want larger patches for the GPU. So we're doing things like we're chaining patches together to put them onto the GPU. And we're exploring lots of ideas like that. Whether or not, you know, I'm not going to tell you right now that we have all that stuff working. If I did, you would probably come along and take away our money and say you can't have the 4 more years worth of money to get this thing to work. Anyway, you know, so there are things that you can do in terms of dealing with that issue. You know, I guess what I'm really trying to say is never say never. You know, there are all sorts of things that we can do. We've dealt with all these other challenges in the past, and I don't see that any of these are insuperable and so on. So, but whether the details, you know, like the size of tasks you want on the GPU, which tasks you want on the GPU, how you get performance for those tasks, are still things that are, you know, that's definitely work in progress. And we have a lot of experience with GPU code as well, but the portability of the GPU code is the issue. And really across multiple GPUs, making sure that you keep the GPU fed is one of the central challenges that we face. And the architecture doesn't help us because of the old PCIe bus. And even NVLink, I don't think will solve a lot all the problems. So yeah, preload tasks and so on.
All right. Thank you very much, Martin.